Hello everyone, this is Solomon. I'm here to explain you about a binary search tree. In binary search tree, we have three types: in order, pre-order, post-order, and we have many others. So now in this video, I'm going to tell you about three topics: in order, post-order, and pre-order. These are the very shortcuts what I have took from some book. To have the insert elements or take the elements, print the elements, so these are very easy shortcuts to remember. So for in order, first the left, next root, and then right. For post order, next root, next left, then right. In in pre-order, in root, left, and right. In post order, left, right, and root. Okay, I need to correct this. Just a second. Okay, so this is left. Okay, I'm sorry for the spelling mistake. So this is left. Okay, so when I take a diagram here, you can see 8, 3, 1, 6, 4, 7, 10, 14, 13. So these are the numbers what I have in my binary search tree. So in this binary search tree, I want to print in pre-order form. So first, we'll go with in order. Okay, in order form. So in order, first we'll go with left, then root, then right. Okay, so L R L sorry, L double R. So we will remember it as left, root, and right. So first we need to go to left. Okay, so this is the root of our binary search tree. So when we go to the left, so this is the left, right. So this is not the child, so this is the parent for these two nodes. So we will go to left for even this. So for one, we don't have anything. Okay, for one we don't have any child roots or anything else. So this is the final one. So first one will be printed. Next, this will come to root. So our order is left, root, and right. So next three will be printed. For 3 is not at all, 3 is the root of these two. So it will come to 6 as it is right. So 6 is not the final number. So this is the root for another two numbers. So for these two numbers, 6 is root. So then we will go to the left of the 6, because we need to go in left, root, and right. So we will come to 4. 4 will be printed. Then it will go to the 6 as it is root for both these. So because 4 don't have any other numbers in right or left. Okay, so it will print 7. 6 is already printed. Our order is 1, 3, 6, 4, and 7. Okay, so next it will come to the root of this. So this side it is finished completely, left side is finished. We'll come to 8. Then 8 will be printed, because this is the root for these two things. Then it will come to the right part. When we come to the right part, this will go to the left, but we don't have any left operator here or left integer, any number. So this is the root for 14. So it will go to the right then. So 10 will be printed. So this will come to the 14. So for 14, it will go to the left, as our order is left, root, and right. So 13 will be printed, then 14 will be printed. We don't have any number right to the 14, so nothing will be printed. So in this way, in order traversal will go. So in order it will travel. Next, if we come to pre-order, root, left, and right. Okay, first root will be printed, then left will be printed, then right will be printed. So this is the root. First 8 will be printed, root, left, and right. So next it will go to the left. So it will come to 3. So this is root. This will be printed. Again it will go to the left. So left. So nothing is there to the 1. So 1 will be printed. Then it will come to the right. 6 will be printed as it is root. Then it will go to the left part. So left don't have any child numbers, so child branches. So this will be printed 4. Then it will go to the right part. 7 will be printed. Next, already 8 is printed as it is a root. So it will come here. Root will be printed 10. It will go to the left. Left has nothing. So it will come to the right. Right is 14. 14 will be printed, and 13. Next it will come to the left. So next 13 will be printed, as it don't have any child numbers or child branches. So it will print 13. Next, it don't have any right child, so that's why it won't print anything. So that's it. So this, in this way, pre-order will be taken. So pre-order. Next, post order. Post order, it is left, right and root. Okay, left number first it will be printed, then it will print the right number, then it will print the root number. Okay, so we'll go to the diagram. So in this, it will directly come to the left part, completely left. So first it came to 3. So 3 is having 2 more child, so it will go to the left of the 3 child, third child. So it will come to the 1. In the 1, it don't have any child branches, so it will print 1. So 1 will be printed, then it will come to the right part, so that will go in this way and come to the right part. But right is having another 2 children, so it will go to the left of the that children. So 4 will be printed. Next it will come to the right part, 7 will be printed, then the root will be printed, that is 6. So this 1 is finished and 6, everything of this block is finished. So it will come to the 3 and finally root will be printed. So this left side is completed. So now we have to go for right side, right? Because root is in the last, so left first, right next, then root. So our left side is completely finished. So now we will go to the right side. So root should not be printed now itself, it should print in the last. So we'll come to the right side. Right side, when we come, so it will go to the left part again. So 10 don't have any left child, so it will go directly to the 14. So 14 is having left child, so it will go to the 13. 13 will be printed, but it don't have any right child, so it will be printing null here, and then it will be printing 14 here, and it will go to the root again to print it. So it don't have left, that's why it came to right. It is printed here and it will print null here. 14 will be printed, go back to 10, and 10 will be printed. So right side completed, left side completed. So the remaining is root node. So the 8 will be printed in the last. In this way, you can differentiate in order, pre-order, post order, and this process will go on all 3: in order, pre-order, post order in binary search tree. I hope you understood what is binary search tree. So now let's go into the code and check code how it's gonna print in binary search tree in order, pre-order, post order. So our class name is node. We are constructing a constructor here. So self x, so self key self dot key equal to x, self dot left and self dot right, because we are having 2 children here, so left child and right child. So we'll keep it as none here. So first we need to insert. So our main code is to insert, delete and display the in order, pre-order and post order traversal. So we are constructing here insertion. So insert r and x, so right and left we need to take. So r equal to none, return node x. So if x is less than or equal to r dot key, so if x value is less than or equal to r dot key, r dot left equal to insert, this will be inserted there. If x is greater than r dot key, then it will go and insert in the right side of the binary search tree and return r. Now we'll go for in order traversal. So when we see in order traversal, we'll take one root node. So root, if root in order root dot left print root dot key equal to end. So when in what we have learned in order left, root and right, so it is going in the same way. First it will go to the left, then it will go to the root, and then it will come to the right. So you can see here, print root key, so left key and right key. So this is the order what it is carried out. So next we'll come to the pre-order. You know, pre-order, first root, then left and right. So you have learned root, left and right. In the same way it is built up here. So in pre-order, next come to the post order. It will go to the left, root and key, left, right and root. So you can see here left, right and root here. So it will go in the same order by printing the elements. In minimum root, so when this is minimum, we need to have some conditions when it is minimum or when it is maximum, how much it need to print, because every binary search tree can have maximum 2 child branches, that's it. Okay, only maximum 2. Either it can have 0 children or 1 children, or maximum at 2 children. It can't contain or it can't have more than 2 children. So that's the minimum case. So minimum case we need to keep here. So temp equal to root, while temp dot left is equal to none, temp equal to temp dot left, print minimum. So this is a minimum, so it can't have more than two child class. Maximum is the same case, so it should have, when it go to the right, if it is a more than two children class, it can't be taken. So if I want to search any element in the binary search tree, we can go. So we are defining a constructor search root comma x. If root is not none, then it need to check root dot key equal to key, where this root dot key will keep on checking the key where it present. So it keep on going in an order and it will check. So I'll just simply give an now how it's gonna happen. So if I want to check 3 in order, so first it will go for 8. Our order is in order. What is our order? Left, root and right. So first it will go for left. So 8 is having right side, it should have less number, and sorry, left side it should have less number than the root, and right side it should have more number than the root. So it will come, what we are searching, for 4. Let us take, so 4 means it is less than 8, so it will come to the left side it came. So this root should be what we have selected, 4, right? So left side the number should be less than the root, right side number should be greater than the root. So 4 is greater than the root, so it should not go to the left side, it should come to the right side. So after coming to the right side, we have 6. So the number what we are searching, that should be less than root if we go for left. If you are going for right, it should be greater than the root node. So our root is 6, right? We are searching for 4, so 4 is less than 6, so it can't go in this way, it can come here. So we can find 4 here. In this way the search goes on. So search operator goes. So we are searching, if root is not none, root dot key equal to key, return root. If root is less than x is less than root dot key, return search. So it will go in the left side. If root x is greater than root dot key, it will go in the right side. So next we'll go for level loaded. So if it is everything is equal, then it comes to the level loaded. If root is none, print list is empty. If nothing is present in the tree, it will print as empty, so it will return back. So q is equal to empty queue here, q dot append. So these numbers what all we give, it should be added to the queue. So while length dot q is greater than 0, print q dot key and end. So node equal to q dot pop 0. So when we want to enter any element into a queue, it should be empty. So when we enter an element, that all elements need to be stored in a queue, that's why we are using append. So append will take the values and store in the queue. If node dot left is not none, then q dot append equal to left side it will store. If node dot right is not none, then it will go and store in right side. So this is the user, what we call is, this is for users. So this is the printing, all what we get in console, these are this. So printing, 1 for insertion, 2 for in order, 3 for pre-order, 4 for post order, 5 for level loaded traversal, next 6 for search, 7 for maximum, 8 for minimum, 9 for exit. So you can go for while true, character is equal ch equal to character equal to int of input. So we are taking input and we are checking condition in if else statement. So if 1, this will go and perform insertion. If 2, it will go and perform in order. If 3, post order, pre-order, 4, post order. In this way this go and works in its corresponding program. So finally when it come for else last statement, if I'm going to enter 100, it's gonna give an invalid input and try again later. So we'll run our example code and let us see how this is gonna happen. What we have taken as an example, let's use those numbers. Okay, first insertion, all the numbers I need to insert. So first we'll take all these numbers and insert in our code. Okay, 831. Okay, first we'll insert 831. Okay, 8 and 3, next one is inserted. Okay, so what you can see here is the address of the element. Okay, the address of 8 is stored in this address. Okay, next 3 is stored in this address, 1 is stored in this address. So this is the address of the node, address of the element what you have entered. So next we'll go for enter our choice. Okay, now I'll enter 1. Okay, what I want to insert. So 8, 3, 1 has been finished. 6, 4 and 7. Okay, 6, 4 and 7 will go with 6, 4 and 7. Okay, 6, 4 and 7 are been also inserted. Next we'll go with 10, 4 and 13. Okay, enter your choice. 1, 10 is the element I want to enter. 10, I'm sorry, I think my code has been entered, so I need to rerun my code. I'm sorry for that. Okay, 1, first 8, then again 1, 3, 1, I'll insert 3 here. Next 1, I need to insert 1, then again 1, I will insert 6, again I will insert 4 there, again I need to insert, so the inserted element is 7. Okay, then 10, 4 and 13, 10, 14 and 13, enter your choice. 1, I want to insert 10, 14, insert again, and 13. Okay, you can see all the elements has been entered, and this is the address of those elements. Okay. Okay, so these are the address of the elements. So now we will go for in order, post order and pre-order. How this is gonna print? So one for in order, our as I said, all the numbers you can check it out here. So I want my choice is 2. So this is the order for in order travel, sir. So I have said you first in order left, root and right. So it will come here, this is the root, so it will come for left, root 3, then it will come here, then it will go for left. So 1, 3, this will come here left, 1, 3, 4, 6, 7, in this way first numbers are. So you can see here 1, 3, 4, 7. So in the same way, if I have explained in the beginning, you can check it out with that. So the exact numbers what I have told will be printed here. So next we'll go with pre-order. 3 with pre-order, you can see here. Next post order, 3, 4, post order, this is the post order. And the next level equal, you can see here. Then we'll go for a searching element. So we'll go with search. Okay, what the enter the node you want to search. Okay, we will see exactly is it gonna come or not. So I want to search 7, so let's check the address of 7, how it's gonna print. So you can see here 7 address and this will be same. So the address both the for 7 and the inserted address and the searching address is same for both 7. So exactly it is searching. So by this you can see. So next, finding maximum and minimum. So I want to find maximum element in the so I gone with 6. Okay, 7 now. So enter your choice. Maximum is 14, directly it's gonna print. So next it's gonna print as minimum. I want to check for minimum 8. So minimum is 1, you can check here. So now we'll come out of the code. So we came out of the code is ended here. So in this way you can code up the binary search tree in order, post order, pre-order, load method. So I hope you understood what is a binary search tree, in order, pre-order and post order. That's all in this video. Thank you everyone.